Okay, I think my screen is visible to you and voice is clear. Then anyone just ping me and confirm me that my screen is visible to all of you. Okay, thank you. So I will resume from the point where we have uh, stopped in the last session. So what we have concluded in the last session, that this is the discriminator and generator, which is getting being trained in an adversarial manner, and generator tries to basically fool the discriminator, and discriminator wants to be very powerful so that it can clearly bifurcate the images which are being generated by the generator network. So for example, we have discussed till this point. So for example, this is discriminator D. So what is the target of the discriminator? It will get input from the two data sources. For example, this is discriminator D. It is going to get input from the two data sources. One is the real data points that are called X, that you can say these are the real images, and one images which has been generated by the generator network. So generator network is generating the images from the noise that is represented by Z. This is the reason what I will say, the images or the data which has been generated by generator network, it is being represented as Z of Z, and the real data points which are sampled from capital X are represented as X. So what discriminator network will get, it is going to get data samples from sources. One is from the real source and one is from the generator. What is the target of the discriminator network? To produce the output equivalent to 1 or nearby 1 for the real images. That means the output of dx should be equivalent to 1 and the output of d of zz should be equivalent to 0, because 1 is the label for the real images and 0 is the label for the fake or generated images which have been generated by the generator. So here what will happen after the training, after the successful training that we have discussed, this discriminator is going to be converted into d of x comma theta, where it is called as parameterized discriminator network, which is being parameterized by theta. What is theta? Theta is nothing but it is a set of parameters that you can say it is set of weights and biases. So what will happen after the training? This discriminator network will have capability to take some input and generate some output. It will be either 0 or it will be 1. Got it? So ultimately it is quite clear that discriminator, the last layer of the discriminator network, is going to give a probability value between 0 to 1, and if that probability is near to 1, discriminator is going to say that this is the real image, and if that probability value is near to 0 or the output value is near to 0, then I will say that this is the image. Got it? Now, if I talk about the generator network, so what is the target of the generator network? So for example, this is generator network G. It is being trained by some random distribution that is called Z. So this is random probability distribution, and the target of the generator is, that is the parameter generator is, that is the trained generator is. This notation represents that Z of Z comma theta. That means it have got the noise, Z, and it is being trained over the course of iteration, and it is being parameterized by theta. Got it? Theta is nothing but set of parameters. So this is a parameterized network. That means you can say that in a nutshell, you can say that it is a trained generator network. And again, I'm saying that generator, and what will be the training set for G? So training set for Z is the noise. Generator starts training from this noise samples only, and I have already discussed in the previous slide. I am repeating it again. Generator starts training from this random noise only, and with the course of iteration, it actually tries to uh, just improve this noise distribution and make this noise distribution that is very close to this actual data distribution. So you can just see that this is 1 and this is 2. This is actual data distribution and this is the noise distribution. So with the course of iteration that we have discussed, generator will try to match this distribution equivalent to this circle distribution that is close to data distribution. How it will be able to do so? For example, uh, generator network have got this input that is called Z, and it has converted this noise. This generator network Z has converted this data into Z of Z. It has transformed this data by applying some functions and converted this data in this form that is called as Z of Z. That means this is the uh, converted noise data samples in some other form. For example, this data set is converted in this form like this. So it is somewhat near to circle. Circle is the actual data distribution. I have just made this for the visualization. Now, what will happen? This is going to feed the discriminator network that this is the generated image. This is the generated image. Just identify whether it is correct or not, whether it is real or generated. Then what discriminator will do? Discriminator, the trained discriminator model is going to classify. For example, discriminator, when discriminator is getting this Z of Z that has been fed by the generator network and it is able to give output 0, that means generator, the discriminator network is able to classify that this is the fake image which has been generated by the noise. This is not taken from the real data sample. That means generator needs to again train itself to make itself more powerful in order to fake this discriminator model. So what will happen? Generator will again train itself. It is going to calculate the loss. How it is going to train itself? It is going to calculate the loss, and using that loss function, it is going to backpropagate, update its weight and biases. Okay? And after updating the weight and biases, it is going to again produce this kind of data distribution. Again, it is going to feed this data distribution to the discriminator, and it will again ask the discriminator whether that these images are real or fake. Again, discriminator is going to produce the output 0. Then what generator has to do? Generator has to again calculate the loss, and again it has to update its weight and biases. That means it had to retrain itself. Again, it is going to produce data discrimination like this. It will keep on doing this until and unless this is not able to fool the discriminator. That means after this point, when I am saying that, for example, after 5,000 epochs, generator Z has converted the data in the form of Z of Z, and this data is very close to the real data distribution. Now, when this Z of Z will be passed to the discriminator network, that is D, when I am passing now this is the fully trained generator network. Now this discriminator is going to produce output 1 for this. That means this discriminator network will is not now able to just bifurcate that whether this image is real or generated by the generator. Got it? So when this discriminator network will produce output at 1, generator will think that yes, noise will be added to actual instances. No. There is a confusion that whether I will start training by adding noise to the actual instances. No, this is not in the case of GAN models. This is the case in the diffusion models. In the case of GAN models, we start with the random noise. You can clearly just see from this figure. I have not taken the actual data samples and added noise in it. I have taken pure noise. Generator start its training uh, with a pure random noise. It doesn't take any labels from the data. I am talking about the original vanilla GAN which has been proposed by the Ian Goodfellow. After, no doubt, after some time there are a lot of GANs, for example, conditional GAN, and there are some GANs which has been introduced for some different purposes. In that cases, we may give some data labels or some image features. But in the case of original GAN, vanilla GAN, we start training from the very scratch. We start from the pure random noise, and that particular noise is again, there is a question: generator should be more powerful than discriminator. That I have already discussed in the last session. It is not the case. Both should be more powerful. Generator will try to fool the discriminator. But for example, generator G is more powerful and this discriminator is not powerful. For example, discriminator is not able to discriminate between the generated image ZZ and the original data sample X. Then what will happen? Generator will give some instances to the discriminator. Discriminator will not be able to discriminator will not be able to bifurcate. And what generator will think? Generator will think that, yeah, I am smart enough and I am creating or I am generating the images which are very close to the real images. So generator's loss will be very, very less. What it will think? Whatever I am generating, it is quite good. So it is not going to train or improve itself, and it will generate the output images which will not be very realistic. So I have also told one example that, for example, you want to win a race and you have three competitors with you. But if you want to win the race and these three competitors are not good enough, then you will not be strong enough. You will just run on the local level, but when you participate in the national or Olympic level, you will not get any chance to win. So in order to be winner, you have to get a tight competition from the discriminator. So what happens? Generator and discriminator both are being trained in a contradictory manner, and the training will continue. So after some time, I am again going to train discriminator. When discriminator is not strong enough, then I am again going to train generator, and like that. So training takes place in a adversarial and healthy competition manner. I think you have got the point. Okay. So again, I'm coming to the main point. This is the generator Z. This is the trained generator model, and this is the reason what I have done. I have taken this random noise and converted this noise into the circular shape. And why it is circular shape? Because I have assumed that the real data distribution is like this. It is in the shape of the circle. It is just for the assumption, just visualize. Got it, na? So generator is going to just convert this random noise into this format, and the now the data distribution is PZ of X. So this is the data distribution which has been given by the generator, PZ of X. Got it, na? And the what is the original data distribution? Original data distribution is P of data X. Got it? So this is the original data distribution, and this is the data distribution which is being generated by the generator network. So my ultimate target is that the generated noise sample should be reshaped to this sample. That means PG of X should now be equivalent to this. This is my objective. This is my intention. Got it? So what will happen? What I have told that discriminator will get the data from 2 points, from two samples. One is from the real and one is from the generator G of Z, and it has to produce output 1 for this and 0 for this. And what is the target of the generator? Target of the generator is to convert this Z into format Z of Z, such that when discriminator is given this input sample G of Z, it should produce output equivalent to 1, not to 0. This is the aim of the generator. Whereas discriminator will want to have this G of Z equivalent to 0. So the objectives of both generators and discriminator are different. What generator wants, that discriminator should give 1 for the random for the data that I have supplied, and what discriminator want, that I should produce always 0 for the fake data. Okay, now coming to the next point. Now understanding the loss function. This is a very important point, so be with me. How to calculate the loss, because the success of the the GAN model is totally dependent on the loss, how you are calculating the loss, because the training or the back propagation is totally dependent upon the loss value, that how you are training your model, how you are training your generator and discriminator network to make the model more and more robust. Got it? So now coming to the loss function. So I think you are already aware about the binary cross entropy loss. So if I talk about binary cross entropy loss, the equation for the loss is y of L of y hat comma y is equal to y of log y hat plus 1 minus y log of 1 minus y hat. This is the equation for the binary cross entropy loss, where you already know that y hat is the predicted output and y is the actual label. Y hat is the predicted value and y is the actual value. This is called binary entropy loss. So if I talk about the discriminator model, for the discriminator, if the data is coming from the, if labels of the data is coming from the original sample, if the labels are coming from the original samples, what I have already told, the discriminator D is going to get the data from two data bases. One is the original and one is the generated by generator network. So if the data is coming from the original data sample, so what will be the label? 1. So 1 will be the label. That means the value of y will be equal to 1 for real data. I have already written these equations in the next slide. These equations are already written, but at this moment I want to just drive in front of you so that you can have better understanding, because this is the main catching point for the generator model if you want to get deep insights. Okay, so what will happen? L of y hat. What is this y hat? Y hat is the d of x. What is d of x? Is the probability value between 0 to 1, which is generated by the, or which is given by the last layer of the discriminator model. And what is the actual output? This is 1. Got it? Actual output is 1. In the right hand side, I will again keep value of y is equal to 1, because this is the real output, 1, and log of, what is y hat? Y hat is dx. Dx means the probability value that has been given by the discriminator network, on the basis of which it is going to decide that whether it is fake or real. Plus 1 minus label is 0. So this 1 minus 1 log of 1 minus d of x. What will happen? This is going to become 0. So finally, this component will be log of d of x. Got it? So this is the first thing, A, that I have got. Got the point? Again, for the data coming from the generator, second point is that this is the first point, that is the data which is coming from the original samples. And second, I'm just changing the color. Second is for the data coming from generator. Again and again, I'm telling you that discriminator is going to get data from the real samples as well as from the generator. So in both the cases, labels will be, actual labels will be different. For the real samples, the actual label will be 1, and for the generated samples, the actual labels will be 0. Got it? So what will be the loss in that case? It has to be L of, I'm putting the value in the same equation, that is binary cross entropy. L of, here what is y hat? Y hat will be d of z of z. That means the probability value of the discriminator last layer on this noise data that has been generated by the generator. Actual label is 0. This will be equal to, first term is going to be 0, because I have to put actual label as 0. 0 cross log of y hat, no issue, plus 1 minus 0 log of 1 minus d of z of z. Got it now? Will be equal to, this term will become 0. This has to be log of 1 minus d of z of c. So I am saying that this is B part. So what will be the total loss for the discriminator? Total loss for network D. What will be the total loss? Total loss will be A plus B, and it has to be A part is log of dx plus log of 1 minus d of z of z. Got it? In color is black. This will be the total loss. The discriminator. Have you got this point or not? Just comment me and let me know that have you got this point or not. This is simple one mathematical equation where I have just written the output values for the discriminator network. Yes. Okay, thank you. So this is the loss for the discriminator network. Now if I will talk for the loss of the generator network, if I will talk about the loss from the generator, what will be the loss of generator G? What will be the loss of generator G? For the generator loss, this component will be constant for the generator. Because this is dependent. D of x is totally dependent on discriminator. So the loss of generator will depend upon this second factor. That is log of 1 minus d z of z. This is about the generator. So loss of generator will be, I am writing here in the top, which is already written in the next slide, log of 1 minus d z of z. Because in the right side, in the equation A, there is no role of generator here, but in the second part, there is a role of generator, because the value of the second component z of z is dependent on the generator network. Got it? Okay. So this is the same thing that I have described by deriving in front of you. This is the same thing that I have already written in the slide. This is the equation of the binary cross entropy. L of y hat comma y is equal to y log of y hat plus 1 minus y log of 1 minus y hat. Okay. The labels for the data coming from the p data x will be y equal to 1, and y hat will be d of x. This is the output generated by the discriminator. So if you put these in this equation, it has to be log of dx that I have derived in front of you, and for the data which is coming from the generator z, this will be equal to log of this plus this. So this is the B part. Got it? This is the B part. So the total loss for the discriminator will be A part plus B part. Now if I want to talk about the generator model, what generator want that this of d of z z should be equal to 1. What it should be? This should be equal to 1. So coming to the same equation, log of d that I have written here, sum of a plus b I am also writing here by changing the in color for your future references. Yeah. Total loss for discriminator d will be equal to a plus b, that will be equal to log of this dx plus log of 1 minus d of z of z. Got the point? So here in the Hello, I think I am audible again.
Yes, sir.
Okay, now is my voice clear?
Yes, sir.
Okay, okay. Yes. My screen is visible to all of you now.
Yes, sir. Visible.
Can anyone just comment and let me know that his screen is visible? Okay, okay. So I think we got disconnected from this point. So I was talking about the loss at the discriminator end. So this is equation A and this is equation B. So the total loss for the discriminator will be A plus B. So it is going to be log of dx plus log of 1 minus d of g of g. So this is the total loss. Got it? So this is the loss for the discriminator. Now if I will talk about the generator loss. So what will be the generator loss? I'm choosing different ink. So what will be the loss for the discriminator? I'm talking about the same equation, that is log of dx plus log of 1 minus dx. So this portion, that is part A, it doesn't have any role for the discriminator because it is totally dependent upon the discriminator. This component is actually dependent on the generator. So what generator will want? Generator want that d of z of z should be equal to how much? Can anyone tell me what generator wants? That d of z of z should be equal to, anyone can tell me? No. Actually, the actual label for the fake image is 0. But if generator has generated image that is z of z, z of z. So what generator want? That if I am giving input to the data, input data z of z into the discriminator d, it should produce output 1. This is the willingness of the generator network. That means this is the wrong classification. Generator wants to fool the discriminator. So if the generator wants to fool the discriminator, that means when the discriminator will be fooled, then discriminator will give wrong classification. So if the discriminator is giving 1 as the output, that means discriminator is not able to correctly classify the data which has been generated by the generator. So when this will produce 1, then generator will be successful. So generator wants that this should be equal to 1. I hope you are getting this point. So if this should be equal to 1, then this whole statement should be minimized. So where we'll get this minima? If you plot the function like this, so it will at this moment of time, at this point when d of z will be equal to 1, this log of 1 minus d of z, this entire function, if I am plotting this function, this will attain minimum value at this point when d of z will be 1 and this number will be fooled. So the idea is quite clear that generator G wants to minimize this factor. Generator G wants to minimize this. Why generator G wants to minimize this? Because generator G wants that the output of d of z should be equal to 1. This is the willingness of the generator. And when this will be equal to 1 and when this factor will be equal to 1, this entire factor will be minimum because this will become 0. And when this will be equal to 0, then this entire factor will be maximum. So what generator G wants that d of z should be equal to 1. That means wrong classification by the discriminator. And when this is equal to 1, so that means this entire component will be equal. When this will be 1, this will become 0. So if this will become 0, that means this is minimum. So what generator wants to minimize this. Where there is no role in this, generator have role in this only, log of 1 minus d of 0. And what discriminator wants? This is the equation for the discriminator D. Discriminator wants that d of x should be equal to. Can anyone tell me what discriminator wants that d of x should be equal to? Anyone? Discriminator wants that d of x should be equal to 1 for the. Yes, very good. Hemant Singh. Discriminator wants that d of x should be equal to 1 because this is the correct, 1 is the correct classification label for the real data. And here what discriminator D wants? Discriminator D wants that d of z, this value should be equal to, anyone again tell me? D of z should be equal to 0. Very good. Now I am confident enough that you are getting the point. So discriminator wants that this should be 1 and this should be 0. Whereas there is no role. Yes, where there is discriminator wants, again I am telling you, discriminator wants that d of x should be 1, that means 1 for the real image, and d of z should be equal to 0, 0 for the fake image. This is fake. This is real. Whereas what generator wants, generator G has no role in this first point. There is no role in this point. Whereas generator G wants that discriminator T should produce output 1 for this fake data. So this is the intention of the discriminator. So both have contradictory objectives. This is the reason what I told you in the initial slides, that they have the contradictive objectives. They have the reverse goals. So this is the reason discriminator D will try to maximize it. Why discriminator D will try to maximize it? Because maximum d of x is a probability distribution function. So the maximum value of d is 1. So discriminator will try to maximize it because maximum value of this one is 1, and here this is 1 minus this, so maximum value will be here 0 because this is in negation. So discriminator wants to maximize this entire component, whereas generator G wants to minimize it because this minima will occur when this d of z will be equal to 1. जब ये 1 होगा, when this will be 1, then there will be minima. When this will be 1, then this will produce minima. So discriminator will want to minimize it. Generator wants to minimize it, whereas discriminator wants to maximize it. I think this point is very much clear to you. Now, if I want to combine it, then this will become like this. The original equation is log of d of x plus log of 1 minus d. I'm putting all the things in the binary cross entropy loss. D of the same equation that I was discussing. This is the same equation that I was discussing. So generator G, there is generator G and there is a discriminator D. So generator G wants to minimize it and discriminator D wants to maximize it. I have just clubbed both the equations in a single equation. Both the generator and discriminator loss have the same equation, but they have the different goal. Generator G wants to maximize it. Why it wants to? Generator G wants to minimize it. Why it wants to minimize it? Because it wants that this should produce output as 1, and when this will be 1, this will have minimum value. And discriminator D wants to maximize it. Why it is so? Because discriminator D wants that it should produce 1 value, which is maximum, because this is a probability distribution function. So the maximum value for the probability distribution function is 1, and it wants that this should produce output 0. So this 1 minus 0, it will have the maximum value, that's what 1. So the discriminator wants to maximize it and the generator wants to minimize it. This is the reason it is called as min-max problem. Both have competing objective. This is the reason this is called as min-max problem. And this is actually the equation for the one data sample. And if you want to make cumulative, for example, in the linear regression, you used to calculate the loss from all the data points with the mean. So similar like this is the loss function for the one data sample. And if I want to generalize it, so I can write it in this form: expectation of log of d of x. This is the same equation that we will get in the paper which has been presented or introduced by Leon Goodfellow for original GAN model. Plus expectation of, this is basically nothing but cumulative sum, d of g of e. So this is for the one sample and this is for the entire sample, where d belongs to probability distribution that has been given by the generator, and x belongs to p of data. That means probability distribution from the original data. So this is the actual equation that has been given by the Goodfellow in his paper, and I hope that you are clear with this loss function, that generator G wants to minimize it and discriminator D wants to maximize it to give the correct output, whereas generator G wants to minimize it so that discriminator is getting pulled. It is given intact. Okay. So I think, do you have any doubt till this point? If you have any doubt till this point, you can just ask me. Otherwise, you can move ahead. Okay, I hope you are clear till this point. Let's move ahead. Again, I'm saying. So if I talk about the training process and probability distribution. So for example, just assume that this is the actual data distribution, this black dotted curve. This is the data distribution that has been P G of X that has been created by the generator, and this is the D function, probability distribution function, that means output of the last layer of the D of X or D of G of Z. That means output of the last layer of the discriminator network. So this is the trained, this is the probability distribution of trained discriminator network. So initially you can say that, you can see that this is the generated data, and this is the actual data, and this is discriminator network. So discriminator network will be clearly able to discriminate between the real and fake samples. Generator will be clearly, discriminator will be able to discriminate. Some epochs, after some epochs, this generator will be a little bit closer to the, this generator will be little bit closer to the real data. So now it will become a little bit difficult for the discriminator. So the discriminator has trained itself, and it is something like this. Now it is something, it is little bit difficult for the discriminator to discriminate between the real and the generated samples. Now after some more epochs, what will happen? Z of Z, that means the data distribution which has been generated by the generator network, is little more closer to the real data samples. Got it? So now it is a little bit more difficult for the discriminator to differentiate between the fake and real data. Now coming to the last point, this is well-trained generator model, and the data distribution of Z and the real data. That means P of X data, probability distribution for the real data, and probability distribution for the generated data is almost similar and overlapping. That's why it is now very difficult for the discriminator to discriminate between the real and generated data. So the key function for the discriminator is something like this, and its value is almost equal to 0.5. So in the initial slides, what I told you, that when D will become equal to 0.5, that means output layer of discriminator will produce probability value of 0.5. Then in that case, now the discriminator is not able to differentiate between generated images and the real images. So we can say that at this point it is quite clear. So it is someone has written, it is the case that what is D value? D value is equal to 0.5. So D value is the probability distribution value in the last layer. So its value is between 0 to 1. At this moment of point, D value is equal to 0.5, and now discriminator is not able to discriminate between real and fake images. I think you have got till this point. Now this is the visual representation that we'll also see in the code, that what is the how the actual data is generated from epoch 1. If I talk about the initial data samples, these are the pure noise, and after by the course of iterations, this noise will be getting converted into the images. This starts from pure noise, that is called Z, and after epoch 1 it is something like this, and after epoch 10 it is something like this. This is just an instance to visualize that how the noise is gradually converted into the real images. So this was also one of the query, that whether it starts with the noise or whether it starts with insertion of noise in the real images. So the answer is again that this GAN model starts training with random noise, with pure random noise, and by the course of iterations, this noise is getting converted into the images, by calculating the loss at all the epochs. Now this Z is converted to this after 10 and after 70 epochs, the images are a little bit clear. And after you can say that 100 or 1000 epochs might be possible. This data is very, very close to the actual images. Now, if I talk about the problems with the GAN, what are the problems that GAN may suffer? So the main problem is that it is not very straightforward to compute probability distribution. If I talk about the vanilla GAN or the original GAN which has been introduced by the Goodfellow, there are two problems. One is the non-convergence and one is the mod collapse problem. One is the non-convergence and one is the mod collapse problem. What are these problems? Non-convergence and mod collapse. Let us see. Non-convergence means कि I am getting the optimum value, I am minimizing the loss, and I am getting the optimum value at which point. So generally, if I talk about the deep learning models, so in this deep learning model, we try to maximize the reward or we try to minimize the loss. Minimize the loss. And what is reward in my case? In my case, reward for discriminator D is that it should produce dx is equal to 1 and it should produce d of z equal to 0. This is the reward for the discriminator. Whereas reward for the generator G is that d of z should produce 1. This is the reward for the generator network. So rewards are contradictory. That I am telling you again and again. So this is the min-max problem. Generator tries to minimize the same function, whereas discriminator is trying to maximize the same function. So it is very difficult to get the Nash equilibrium. What is the point where we can get an equilibrium, where we can get a clear-cut consensus between the generator and the discriminator? So generally, this problem is kind of multi-objective problem. So this problem is actually multi-objective problem with two objectives which are contradictory to each other. And majority of the time, the deep learning problems are single objective problems where we used stochastic gradient descent. SGD generally tries to find the global optima and it gets success. Where in the case of GAN model, this is a multi-objective problem. We have two objectives which are competing with each other. It is very difficult to get the optimum value, which is global in nature. So if I will try to if you will try to understand this with example, we can see that this is min-max function. Some function is like x into y, which is dependent on x and y variable. So one wants to maximize it, D wants to maximize xy, whereas G wants to minimize x and y. For example, the value of x and y, and the value is dependent on two variables that is called x and y. So if the value of x and y, if the both values are greater than 0, so in that case, this function v will be greater than 0. So what generator G wants? Generator G wants to minimize this. So in order to minimize it, what generator G can do? It may just make this value of x less than 0. So when the value of x is less than 0, after decreasing it, decreasing x, then this v will become less than 0. If v will become less than 0, then what discriminator will want? It will try to increase it. In order to increase it, again, what generator can do, it may again make this value from y greater than 0 to y less than 0. So again, it will become greater than 0. Again, discriminator will do it less than 0. Again, generator will make it less than 0. Again, discriminator will make it greater than 0. So because objectives are contradictory in nature, generator is pulling the row in the opposite direction to as that of discriminator. So it is very difficult to get a Nash equilibrium. You can also see this with example, with this figure. This is the value of x. This blue point is x. This blue is y, whereas red is X. So you can see from the figure, when the value of Y is above the Y-axis, the value of X is below the Y-axis. And this product X of Y is getting a lot of oscillations. We want a point where we can satisfy both the generator and the discriminator. So after some time, these oscillations are getting more and more. All these objectives are contradictory in nature. So I think you have got the point, because this is multi-objective problem. So it is really difficult to get a global optima, because generator wants to minimize the same objective, whereas discriminator D wants to maximize the same objective function. Now coming to the second problem, that is also called as mod collapse problem. This is also one of the very popular problem in the case of GAN. This is called as mod collapse problem. What is this mod collapse problem? Mod collapse problem is basically, we can see that after in some cases, after some epochs, generator G generates similar type of images. That means in some of the cases, what happens? Generator G is not able to generate the diverse data samples. Generator G is not able to generate diverse data samples. What happens? The output, what is expected, that it should generate diverse data samples, whereas what happens? It is stuck in some type of output samples and it is producing some particular type of images. Let us see by one more example. Like this is the input data sample. What is my expectation? That generator G should produce all the types of images in the output, whereas what happens actually, it is producing only some type of images. Might be possible it is producing only 3, 4, and 5, and it is not able to generate rest of the other digits. Or for example, I have given 10 kinds of faces or 15 kinds of faces. I want to generate diverse faces. This is my expectation from the generator. However, as a matter of fact, it is able to generate only 2 faces. It is generating similar kind of faces. This is called as mod collapse problem. I hope you have got the point. What is mod collapse problem? Mod collapse problem means generator is not able to generate diverse data. It is generating some similar type of images, whereas as a matter of fact, my data distribution is diverse. We have 100 type of faces. My expectation is that generator will generate 100 types of images, 100 types of faces, whereas it is generating only 2 or 3 faces. This is called as mod collapse problem. And why this mod collapse problem happens? What is the main problem because of which this happens? This happens, for example, the real data distribution is again multi-model. This is called as multi-model function, where we have multiple peaks. Got it? For example, this is a multi-model function. This is also have generator G have generated data distribution like this. Multi-model function means the actual real data distribution have multiple type of probability distribution. This probability distribution is different, this is different, this is different, because for different kind of faces we have different probability distribution. However, as a matter of fact, generator Z has generated probability distribution like this, P of Z of X. This is the probability distribution which has been generated by generator. And generator, my discriminator is not able to bifurcate this. It is producing one for this. That means my discriminator is not able to predict or classify correctly that whether this face which is being generated by generator is real or fake. So what generator will think? Generator will think that yes, I am successful and I need to go in that direction. So what will happen? It will try to make probability distribution in the same way as it is doing. It is not going to correct itself. So that means the loss is very, very less. So if the loss is less, then what generator will try? Generator will try to do the similar kind of data distribution. So what will happen? It will keep on enriching this type of data, probability data distribution, and it will keep on generating similar type of images. Whereas if generator is getting failure, then it will try to change its probability distribution to fool the discriminator. So what generator will, if generator is not getting failed, it is easily able to fool the discriminator, then what it will do? It will generate the same or similar type of image, or it is going to generate some group of images from which generator is able to fool the discriminator. So either it is going to generate one type of image, or it is going to generate 5 types of images, because from this set of 5 images, generator is able to fool the discriminator. So this is called mod collapse problem. So I think, are you clear with the mod collapse problem? What is the mod collapse problem? Can anyone just ping and let me know that have you got this mod collapse problem or not? I hope that my voice is audible to all of you. Yes. Yes. Okay. Yes. Yes. Okay, that's good. That we are clear with the mod collapse problem. Again, I am summarizing that mod collapse problem means generator Z is able to fool the discriminator with 1, 2, or 3 or some subset of the images. This is the reason generator is quite happy that I am skilled enough. Yes, very good, Hemant. So generator is quite happy that I am skilled enough to fool the discriminator. So it is not going to diversify itself, and in future it is going to generate similar type of images which is not the required. Yes. Now I will be a little bit quick. Let us see that what are the real life use cases of the generator. If I we have already discussed in the first session that what are the real life applications. So for example, if we want to generate some deepfake images or some duplicate images, then we can use it. It is image generation. Second use case is image to image translation. Image to image translation means, for example, I want to make photo from this sketch, then we can use image to image translation. Or I want to painting of a photo, I will input a photo and I want painting of that photo, then I can do this image to image translation. So for that, cycle GAN is actually used. Cycle GAN can be used to convert one type of image to another type of image. For example, I want to make horse from the zebra, so I can use cycle GAN to convert horse from zebra or vice versa. A very popular application of the GAN is that is called resoluting the image. So we have already discussed that if we have a low resolution image, in the beginning of the session, I have discussed one of the application of the AI, that if I want to de-age image, if I want to convert an image from low resolution to high resolution, so that is quite required for data processing in extreme weather conditions, as well as data processing of the medical images where we don't have very clear images, or we have some satellite images and we want to improve the resolutions of those satellite images. In that case it is quite good. So we can use SR GAN. SR GAN is super resolution GAN, which is being used to resolute the images. That can be a very good research problem. Data augmentation, we have already also discussed. We have also given some example in the case of agricultural images. That can also be a use case of the medical images. We have some minority class, and if you want to increase the samples of the data for training, then we can just use GAN models to create some duplicate images which are very close to the real images, and we can just upsample my data for the better training of the model. No doubt, this is also one of the very wide application. Text GANs that we are using, our generative models are able to generate the text for us, that you are quite aware. For example, generating some reviews or some other data. So these are the major applications of the generative adversarial networks. And if I talk about some of the popular networks, so we have vanilla GAN. This is the GAN that we have discussed, that is given by the Goodfellow. This is the basic network which uses multi-layer perceptron along with the conditional GAN, deep convolutional GAN, super GAN, and cyclic GAN. And nowadays, no doubt, today we have more than thousands of GANs because again there is a free lunch theorem. Everyone is trying to make a generative adversarial model for his own requirement, for his own data. So there is no restriction. You can generate. You can have your own network architecture. You can have your own generator. You can have your own discriminator. You can have two generators. You can have two discriminators. You can have three discriminators and two generators. There are a number of opportunities for the researchers in this area because this is really interesting and evolving. But if I talk about the vanilla GAN, this is simple GAN, which has been given by the Goodfellow in 2014. So basically, this is used for the educational purposes. It is not good for some generating some real faces. It is something good for the gray level images and basically like MNIST dataset and fashion dataset. So not good for high resolution image generation. So I have also written in my PPT that where it is good and where it is not good. So vanilla GAN or basic GAN that we have studied is good for the educational purpose to understand, and it is good for the basic grayscale images. However, it is not good for complex and high resolution images because the generator and discriminator model, simple multi-layer perceptron model. So these MLPs are not good enough to understand complex images. Again, if I about the vanilla GAN, so these GANs are good for such kind of applications to generate such kind of images like the MNIST data set or fashion data set. Talking about a cycle GAN, that I have already told you, cycle GAN is basically used for image to image translation. We can just have image to image translation, like we want to convert photo to painting and we want to convert summer to winter, or if you want to convert day to night. In that case, we can use cycle GAN. And basically, if we see the real life use case, then we can just use converting day to night scenes that can be helped for self-driving cars. And we can use this for the style transfers. For example, turning photo into some different kind of styles like paintings or some scene or some other kind of things. Basically, if you see that this network has two generators and two discriminators. So for example, this is the real image in domain A, and this is the reconstructed image of A. So for example, I want to just convert this zebra into the horse, then we can just use this model. So basically, there will be two kinds of generator and two kinds of discriminator. This generator, one generator will be used to generate images like this, and one generator will be used to generate images like this. So you can just go into the details of this cycle GAN as and when required, depending upon your requirements. Coming to the conditional GAN. So basically, if I want to produce the output based on some conditions, for example, I want to generate X-ray images of the patients, and if I want that, I don't want the images with pneumonia. I want to generate simple healthy images. In that case, we can give the condition along with the input. That's whatever the image you have to generate should not have pneumonia, with or without pneumonia. And similarly, and vice versa, we can also give input to the generator along with the label this is the label that you have to produce. You have to produce the images with pneumonia, or you have to images without pneumonia, and vice versa. So conditional GAN means we are giving some condition to the generator for generating the images. For example, I am giving the condition to the GAN that we have to produce black and white images or grayscale image, or you have to produce color image. So we can give input to the generator model. For example, if you see the case, this is the generator model. So initial in the traditional GAN, I am giving just noise as an input to the generator, whereas in this GAN, we are also giving labels to the generator model. So along with the noise, we are also giving labels to the generator model. So it is producing the output based on the labels. So just see the example. This is the input image, and this is the output image. So again, if I want to convert any black and white image to the color image, we can give the condition to the generator that you have to produce the color image, and on the basis of that, this conditional GAN is able to produce color image that of from the black and white image. So this is basically the image reconstruction. Now I'm talking about the DC GAN. So what the limitation of simple vanilla GAN? I have told you that it is not good for the complex images, because the generator G and discriminator D are the simple multi-layer perceptron model. But if I am using some deep networks as a generator and discriminator for processing the complex images, then this is called as a deep convolution network. So for example, if you want to generate fake faces or avatars from the media, so for generating such complex images, we need DC GAN, where you can have your discriminator and generator. Like some pre-trained model can also be customized as per your requirement to make the generator and the discriminator. So there are a number of opportunities to change the generator and discriminator. So this is about the DC GAN. Now the last one, that is called super resolution GAN, that is called SR GAN. So the basically SR GAN is used for increasing the resolutions of the images that I have already told you. For example, I have some satellite images with low resolutions, or we have the images which has been taken remotely that have low resolution. In that case, we can use SR GAN. It can be used to enhance the resolution of the image for making those images quite clear. So if you want to see the example, for example, I have cropped this image from this image has low resolution, and I want to increase it. I may do it like this. I have just this is the low resolution image. I have converted this to the high resolution image. Again, this is low resolution image. I have converted this to the high resolution image. So basically, SR GAN is used to increase the resolutions of the low resolution images. So these are some of the basic applications of the generative adversarial networks. Now we can just have some hands-on with the generative adversarial networks. So what I will do, I will share a Kaggle notebook with you. You can just open that link, and I will keep on telling you that what is the functionality that I'm achieving by that. Yes, I will give link here. Okay. I hope everyone have got the link and open this link. This is a Kaggle notebook. Just click on, yeah, that's good. Just click on edit in the right hand side, edit my copy. You have to click on the right hand side, edit my copy, one thing. And another thing is that just check that in the right hand side that your internet is on or not. This should be on in order to get the access of the GPU from the Kaggle. This should be on. So make it internet on. And if you are not able to do it, then just click here and just link your mobile number with this one. Unless and until you will not link your mobile number with this Kaggle, then you will not be able to access the GPU. Again, I am telling you, you will just see the right side of the notebook where my cursor is. Just make sure that your internet connection is on. If it is not on, then connect your mobile phone with this. You have to click on the link which will show in the right hand side. It will be verified by the OTP. You have to connect your mobile and make this internet on. And if you are not able to do this at this moment, I will share this notebook with you. You can do it by yourself as a home assignment. Got it? So if you are able to do it, then just try to run the cells with me in order to visualize the code. So the first cell is the I am just importing all the packages. So basically, this is a simple line. Whenever you will click it, and it will be connected with the GPU. Draft session is starting. Yeah, it is connected with GPU now. Session has started. So I have just imported all the packages. In the second cell, just see that what I am doing. I am just loading the data. Dataset.mnist import data. And what I am doing, I am just loading the data in two parts. There are two variables. One is the train X and one is the train Y. So I am just making the training and testing samples of the data. So this is the input features and train Y. This is the output labels. So we can see that in the training model we have 6,000 images. In the test model we have 1,000 images, and the dimension of images 28 cross 28. I'm just giving you a brief overview of the code. You can just do it at your home with your own exercise. Now what I will do, I will just importing a PyPlot. I want to just show some sample images. So what I am going to do, I am just taking 25 sample images, and I am making a grid of 5 cross 5 to show the sample images. I'm running this cell. So in this cell, what I have done, I have taken a sample of 25 images to know about my data, that how my data looks like. So this is basically MNIST data set. These are the handwritten digits. So these are the 5 cross 5 images. Grid of 5 cross 5, showing the sample images. So I am taking the training images and train labels. So these are the training images. These are the train labels. Okay. This what is if you see about this cell, this buffer, this is the buffer size and this is the batch size. Why batch size is used? If you want to process the data parallelly, so we can just feed the training data in the batches of 56. So these batches of 256 will be processed in parallel, because in the backend I am using CUDA and the GPU. And this is the buffer that is going to save the intermediate images, so input and output. So by taking a buffer, you can just save some IO operations to speed up your process. I hope that some of you are able to run this with me. So let us make the generator model. So generator model, what generator model will do, I have already shown you in the beginning of the slides that what generator model is going to do. The first layer for the generator model is dense and reshape layer that I have already shown you. That after getting the noise, what generator does, the first layer is dense layer followed by the reshape layer. It is going to convert 1D noise vector into the desired image shape. So basically for that purpose, dense layer and reshape is used. After that, what we did, if you will again see the PPT, we have applied several convolutional 2D transpose layers in order to upsample the data. For example, my data sample was initially 7x7, and after that, I just upsampled that data, increase the dimensionality of the data. So basically, this is the generator layer. So finally, I have also written the comments that upsampling to 14x14 and then again upsampling to 28x28. So for upsampling, I am just using solution to the transpose. So this is the first image sample that I am calling this make generator model, and it is going to generate. It is going to show you the image that has been generated by the noise. Yeah, just see. Training is false. That means at this point I am not performing any kind of training. I am just what I'm doing. I'm just printing this image that has been generated by the noise. So this image is without training. Means this is the input image that we have given in the first typo. And this is also to one. This is also the answer of one of the question that someone has asked, that whether we are giving some image plus noise to the generator or we are giving pure noise. So you can see that this is a pure noise. This image don't have any image features. This is a pure noise because training is false here. Now making discriminator. This is the discriminator model. What discriminator model will do? It is going to apply some layers like convolution 2D layer, and finally what it will do, in the last layer it is going to flatten this to make it again 1D. So what we have did in the generator network, we have just converted image from 1D noise to 64x64 or 28x28 2D image. And what we are doing in the discriminator, we are just again processing that image in reverse and making it 1D, because in the last layer what we want probability distribution. So for that we are using sigmoid as a activation function, which is going to give the value between 0 and 1. So this is the discriminator model. So if you try to see the decision of the discriminator model, because what I already told you in the during the PPT, that discriminator model, the last layer of the discriminator model produces d of x. And what is d of x? D of x is the value, probability value between 0 to 1. So you can just check that what discriminator is producing. Discriminator is producing the probability value between 0 and 1. And I have also told you in during the session that what is my ultimate aim, that what should be the value of dx for the discriminator. So it should be around 0.5. So when the discriminator will produce the value of d as 0.5, then that it will signify that generator is able to fool the discriminator. This is cross entropy. This is binary cross entropy loss function. So we have also used during the session. I already discussed in detail about the binary cross entropy loss. I am using same loss function that is called binary cross entropy loss. Okay. So now look this cell very carefully. In the slides, what I told you, discriminator will get the loss from two data samples. One is the real samples. It will get few images from the real samples, and it will get few data samples from the fake. So this is the loss. I'm calculating the loss by getting the real samples, that is real output, and this is the loss of the fake outputs. So this is the real loss and this is the fake loss. So total loss is real loss plus fake loss. If you remember, while calculating the loss, I have already shown you that there are two things, A plus B, where A is the loss of the samples that we are getting from the original data, and B is the loss from the samples that we are getting from the fake data. So this is real loss and this is fake loss. Got it? And this is total loss. I hope you are getting this point. Can anyone let me know that you are getting this point or not? Why this is real loss plus fake loss? Okay, if you are not aware with this, you can just go through again with the PPT, where you can just see that what is the meaning of the real loss and fake loss. And this is the generator loss. For the generator, we have only one type of loss because it is getting the data only from the noise. It is not getting any input from the real data. So we have to calculate 1 minus dz of z. So this is the fake loss that I'm telling. This is the optimizer. What I already told you that we want a global optima where we have the minimum loss from the generator as well as from the discriminator. So we have to call the optimizer. So for that we are using ADAM optimizer. I think this is the basic, very basic code. You are able to just get it. This is some of the checkpoint that I'm making on the training so that we can resume it back. I'm running it for the 50 epochs and initial noise dimension is 100. No doubt that this noise sample will be upsampled by convolutional 2D layers that is being used by the generator. This is the training function. So for the training functions, I am just passing the training data and training labels to the generator. And we are calculating the real output and fake output plus generator loss and discriminator loss. So by calculating the loss, we are just back propagating. This is the thing. So this train function is following this train step by passing these mini batches. So mini batches are nothing but, for example, I have 100 images. I had made a batch of 25. So those batches of 25 will run in parallel because we are using GPU and CUDA in the backend. So we can do some kind of parallel processing. So this is to generate and save images. So in the output folder, what I'm doing, I'm just saving some images that you can see in the right side. That I will show as an output in future. So if you want to just check that how the images are being generated, we can just run this train function. So this is going to show you the output epoch by epoch. Might be possible some of you are able to run this code along with me. This is quite simple, and if you want to know about the syntax, you can just copy and paste that particular line in the GPT. Yeah, just see. This is the output for the epoch 1. In the first epoch, the output is something like this. And you will see that by the course of iterations, how the images are being changed. Yeah, This is the output after the second epoch. That means we are getting some better quality of images in the second iteration. I hope you are getting some interest in this. This is output after the third epoch. So I have just shown the outputs of the 5 epochs. You can do some hands-on with yourself to just check that how the generated images are basically improved by the course of iterations. So I'm running here just 5 epochs, and after that, yeah, this is the output after the 5 epochs. I have run only the 5 epochs, and you are able to see that after 5 epochs, we are getting some visibility in the images. So you can run all the epochs. For example, if you are running 100 or 50 or 200 epochs, after 200 epochs, you will be able to see quite clear images. No doubt, this data is quite simple. That's why you will be able to see good quality images after the 5 epochs. Otherwise, if the data is complex one, this training process is going to take a lot of time. No doubt at all. So if you see the images that I have generated, these are the saved images because I have already run the code. So you can just see after these epochs, after 16 epochs, after 30 epochs, I can also show you this in folder. Epoch images that I have already shown. Okay, I think my this screen. Let me share the entire screen. Yeah. See, this is image at epoch 7. This is image at epoch 52. So you can see that after 52 epochs, we are able to get very clear images. So in between, if you want to see the images, you can just run the code, and otherwise, if I will show you the image at epoch number 16, just see. This is the image at epoch number 16. Got it? And I have run it for, I think, 50 epochs. You can see the image after 52 epochs. After 52 epochs, we are getting quite good image. No doubt, this data is quite simple. That's why we are getting good quality image in the 52 epochs. However, if the image is complex, again, we have to do quite hard training in order to get a good result. So I hope you now have a good acquaintance with the generative adversarial network. If you have any questions in your mind, you can just ask me. Otherwise, we can end the session and you can go for the lunch. Okay, I think we are done with the today's session. So we can end this session right now. You can go for the lunch. Okay, thank you all of you.